cubic foot of volume inside, right? Because we have a clear understanding of the geometry. Inside something like that, there cannot be too much space, because we know geometry, Euclidean geometry. Well, except that Euclidean geometry doesn't describe real space, because real space is described by this curved geometry. That's the core of Einstein relativity, and gravity itself is this distortion of space and time. So what's the geometry inside a black hole? Basically, is enormously larger than what you expect. So when you go in, you find a huge space inside. You remember these fairy tales? You go in the forest, there's a teeny hut, okay, small. You go in, and then there's a huge room, another huge room, and gardens, blah, blah, immense space, and you go out, there's a teeny hut in fairy tales. Well, the universe is a fairy tale. It's exactly like that. That fairy tale is more realistic than our Euclidean space. And the shape of the space inside, I have another tool here, that's my tool. This is a lower dimensional analogous. Imagine you have this circle here, and I say this circle bounds a surface. This is a few centimeters. What is a surface? Well, it's just a few centimeters square. No, look, surface much bigger. You can imagine this can be a very big surface. So that's exactly what's inside the black hole. It's like a long tube, which is very, very long in one direction and small in the sort of the radial direction. So once we go in, there's a huge, huge thing inside, but small. Last reliable thing, everything I've said so far, every good relativist would agree. I mean, there are a lot of relativists in the room. I hope I'm not saying anything wrong. This is for the specialist, I'm using maximum volume foliation inside the black hole, just in case there's some technical thing. So every good relativist would agree that what I've said is credible, reliable, and that's what Einstein theory predicts. And Einstein theory has been so good so far, which no reason to, I believe, to doubt it. So last surprise, given by Einstein, we are inside this long tube, okay? And we discover that this geometry in which we are is not static, it's changing. And it's changing how? It's becoming longer and longer as time passes, which okay, but worse, it's shrinking. So we are in, we cannot go out, and it's shrinking around us. And then we say, oh boy, okay? And in fact, I mean, if one wants to be realistic, even if we go inside a huge black hole like this one, or one of the bigger one, pretty fast we find it shrinking, and there's this long direction in which we're pulled long, and we're spaghettified, right? We are squeezed in one direction, in two directions, and elongated in another direction. Good. Now, we shrink, and then what? And here's the point. Then we cannot rely on Einstein theory anymore. Because a simple calculation that every physicist could do is that if you want to know when quantum mechanics comes into phenomenon, you can do an estimate. And what you get is that as long as things are macroscopic, are big, you can forget quantum mechanics, right? This big ball, just forget quantum mechanics. But when things start becoming small, or very high energy concentration, or great curvature, quantum mechanics comes in. And the quantum effects on this dynamic of space-time are quantum gravity, is what we still don't know. This is what I've been paid for doing all my life, for decades and decades, right? But I've worked with the theory, with people here in PI, a lot, Bianca, Lorana, a lot of postdoc and students, and Lee Smalling and many others. There is a theory. We have a very good theory, which I believe it firmly 3 days a week. And the theory tells us some prediction, which might be right, but the theory might be wrong. So now I'm going to tell you what I consider the best possible quantum gravity theory. Tell us what's going to happen next. But now I have to change gear, because so far I keep telling you, believe it, it's reliable. Now I cannot say that anymore. Now I say that's our attempt to look beyond current knowledge. Okay? So what happens? Well, quantum mechanics, what does quantum mechanics tell us? That the world is granular, photons is just photons, light is not continuous, this is grain. There's an atomic structure of things, quantum fields have quanta which are particle-like. So space-time itself should be granular. That's one of the main predictions of quantum gravity. There's a minimal size of things. That the dynamics is probabilistic. So you cannot follow exactly equation tell you what happened, but you have probabilities. And you have probabilities of jumping. Remember the quantum jumps at the beginning of quantum mechanics. Electrons stay on orbits but can jump from one orbit to the other. And you can compute this jump, and you can jump from one classical story to another classical story. A typical example of a quantum jump is the tunnel effect. If you have a wall and a particle that can bounce on one side and can bounce on the other side, quantum mechanically you can bounce from one to the other. You tunnel through the wall. So what can happen when this geometry shrinks? You might get to tunneling into some other solution of generativity, some other classical. Which solution? And now I would like you to guess. And I'm going to help you. A black hole is formed, most black holes we know are formed by collapsing stars that fall into itself. We, with our starship, have been falling through the black hole. The shrinking of the black hole is really a falling. It's like the space-time falling over itself and closing into itself. Now, when something falls and hits something that cannot go over, because you cannot squeeze too much, there is a minimal size, what happens? When something falls and finds a barrier, what happens? It bounces. Okay? The typical things that happen when you fall and you hit something, you bounce. So that's the idea. At the end of the shrinking of the black hole, there might be a bounce. A bounce into what? Now, if you look at the bounce of this ball, the coming up is very similar to the going down, except that if you make a movie of the going down and you project it backwards, you get the coming up. So a bounce, it's like a movie reversed of what happened before. It's a time reversal of what happens. So that's what could happen, okay? This dynamical squeezing and coming longer of that could jump into a reopening and coming back or whatever inside. Now, question, could that be again described by standard Einstein theory? Yes. In fact, Einstein theory has a solution, which is a black hole, which is this shrinking, and has another solution, which by lack of imagination is called white hole, which is exactly the time reversal of that. Now, if you look in books today, they say, well, white holes don't exist. This is a solution for Einstein equation. Okay. Maybe. Why people don't expect that white holes don't exist? Because how could they be born? You see, in a black hole, things fall inside. If you think the opposite, a white hole is something out of which things come out. Right? If you make a movie of water going to a bottle and you do the movie backward, water comes out of a bottle. So people say, come on, white holes would be, things coming out from a sphere. Where do they come from? Well, they could come from a black hole, which has bounced quantum mechanically, has become a white hole, and come out. So the suggestion that comes from quantum gravity and from the theory of loop quantum gravity is that this is a possible phenomenon. A black hole shrinks, becomes very long, jumps into a white hole, and then things come out. But careful, that's a first picture. Let me make the picture more precise. I'll let this go. Does it come out exactly like it went down? No, right? Why? I mean, I let it go up to here, and it only comes down here.